So sufficient penetration and subject contrast, how they're affected by kilovoltage. So let's see what we say here. The most important function of kVp is to provide at least partial penetration through the body's tissues, right? If your beam energy is too low, no amount of mass can compensate for that. It's a really important sort of one-liner to remember, right? It's right here, actually. No amount of radiation, MAS, can compensate for insufficient kVp. If your kVp is too low, you will not have an image because the beam doesn't have enough energy to get through the body. Okay, every body part has a minimum beam energy. A minimum kVp for penetration. Like, for example, hands, it's something like 54. Okay, other body parts, in the chest, we think of like at least in the 80s, right? No one's setting 60 kV for a chest X-ray because there's a minimum penetrating power for the beam, and you can look these up. We have them in the textbook. There's always a minimum beam energy. So this is 6 radiographs taken? Let's see what they say. A through E, all of them, were taken at 30 kVp. What did I tell you the minimum was for a hand? Like 50-ish, 54, I think is what I said, right? All of them taken at 30 kV, so kV is the same, all with increasing MAS. A was done at 45 mass, 90 mass, 180 mass, 360, 720, and then G was done at a higher kV. Anyways, let's look at A through E. All right. Can we see? Do we have visible structure in really any of them? Not really, right? All of them, with maybe some of the exception in E, right? I have no visibility of my structures. I can't tell adjacent structures apart because there's insufficient penetration. The X-ray beam was absorbed equally by all of those structures because our beam energy was too low. No amount of increasing mass really compensated for that, right? Underexposed, and notice you see model here now too, right? Model's going away because we're adding more mass, right? But we never have enough penetration to adequately penetrate the hand and adequately show us bony detail, soft tissue structure detail. It's all lost because there's not enough signal in the remnant beam, the beam that has passed through the patient. How do we fix that? Mass isn't going to fix it. We have to set the right voltage, kV, okay? So kV can sort of make up for mass insufficiencies, but mass insufficiencies can never make up for kV insufficiencies. You've got to set the right kV for every body part. As kV increases, as long as you get above the minimum necessary for penetration, then as kV increases, more different types of tissues are penetrated differently, okay? Bone gets penetrated differently than muscle, muscle differently than fat, fat differently than air. And now you can start to tell the difference between adjacent structures, right? In this previous image, you couldn't tell the difference between adjacent structures in these because there's not enough penetration. But after you get past enough penetration, changing kV lengthens grayscale. Raising kV lengthens grayscale. So, let's turn the lights down a little bit. Top left image, low kilovoltage. As you raise kilovoltage, and it's not hugely apparent here to here, but as you raise kilovoltage, big differences are shown from here to here. I add more shades of gray into the subject contrast. I get a longer grayscale in image 4 than I have in image 1. More shades of gray because I have a beam now with a higher kilovoltage. Higher kilovoltage gives me a wider range of energies, okay? And now all those wider ranges of beam energies can now penetrate all these different tissues differently, okay? So instead of, just black lung and white every other thing, right? I get lung field that shows me lung markings. I see a sort of a difference in the top of the lung field to the bottom as far as density brightness, okay? And now I can start to make out that there's structure, something behind the heart, where I definitely can't in at least the first 3 of these, okay? Harder to see, but now I can start to make out there's an air-filled trachea here. harder to see, I'll grant you that, but it's there. I can begin to see that I can notice rib. This rib follows. I can sort of follow this rib to behind the heart. That one too, that one too. We've penetrated the heart now. The heart, which was not penetrated, now gets penetrated. The heart's a muscle. Now we're penetrating the muscle a little bit better by just adjusting beam energy. So that's the thing, is that these were all done by adjusting kilovoltage. I got right real quick. Not by adjusting mass. Adding shades of gray, that's the idea, okay? High kV equals low contrast equals long grayscale. High kV, low contrast, long grayscale. Low kV, high contrast, short grayscale. Here we are, minimum kV for body parts, okay? This is the minimum necessary for body parts. I bet you have this right in your textbook. Let's take a look at what they look like. Oh, I can't zoom in. That's dumb. So let's take a look at these. These are not the optimum kVs. These are the minimum necessary, right? When you do a hand, wrist, digits, right? 54 for those structures. What do we usually set for like a hand? 65, 70, 60 is what I'll normally set, right? Those are all above the minimum, right? Really, nobody's setting 50 kV for a hand because it's below the minimum necessary to penetrate the hand. It's close, but it's not that close. Notice till we get to from the hand to like an elbow, right? The elbow is bigger than the hand, thicker. Just by thickness, it's thicker. So more kV for that thicker part. Ankles and legs, usually thicker than forearms, so more kV. Come down to like, what do we want? A chest x-ray. A chest x-ray done without a grid. We've talked a little bit about grids, no more than others, but a chest x-ray without a grid, 80 kV. Chest x-ray with a grid, 120 kV. The grids absorb scattered radiation and some of the useful beam, so more kV, more x-rays passing through the body, higher kilovoltage, more x-rays pass through, there's more there now. And it just goes like that. Usually the thicker or denser the body part is, the higher the kilovoltage necessary to penetrate. Again, these are all minimum necessary kilovoltages. Notice how a lot of them, if you look sort of in the middle-ish, this whole middle range, from skull all the way to like knee, all of these are right in that sweet spot, the 70 to 80 kV sweet spot, okay? We'll find that many of our body parts, we sit right around 70 to 80. That's because most body parts have a minimum of that much, okay, minimum necessary. Less for the very small things, more for the very large or very dense things, like air contrast with barium. Barium's very dense. Barium doesn't make your body thicker, it just makes your body denser in that area because barium's a very dense material. Esophagram, solid column barium studies are all using radiographic contrast materials that will add density. So we have to use higher kilovoltage for these. But just this kind of sweet spot right in the middle. Okay. The thing to get out with this next part is when we make kV changes, we can make kV changes that are sort of have an equivalency to mass changes, okay? So mass can't make up for kVp. That can never happen, okay? But kVp can make up for insufficient mass. It's a one-way street. It can't go both ways, okay? So here's the thing to remember though. You can use kV to make up for mass, but the relationship between kVp changes, how they relate to exposure at the receptor, is not direct and proportional like mass was, okay? If you doubled kV, it does not double the receptor exposure. It increases the receptor exposure by a whole lot more than double, okay? Because there's sort of an exponential relationship, not a linear relationship to intensity. Okay, So let me just give you the simplest possible thing to think about. A simple formula would state that for every 15% change in kVp, the exposure at the image receptor doubles. Okay, so as you go up 15% in kV, image receptor exposure doubles. Importantly, image receptor exposure would double without doubling patient exposure. That's a huge, huge key, because if you wanted to use mass to double the exposure at the receptor, what do you have to do to mass? If you wanted to double the exposure at the receptor, what would you do to mass? Someone heard it from this side? Nobody?
Oh, 50%.
No, with mass. If you wanted to double exposure at the receptor, how much would you have to change mass? Let's say the mass was 10, and you wanted to double receptor exposure. 30% would be the minimum to notice a difference.
50 to 100%.
You have to change by 100% to double receptor exposure. Remember, this is just the subject of the last thing we talked about before we switched to this lecture note. Mass changes are direct and proportional to exposure. If I double the mass, I have doubled the patient's exposure and I've doubled the receptor exposure. Because mass is just controlling how many x-rays are in the beam. You double the mass number, you double the number of x-rays in the beam, right? This is not controlling the number of x-rays in the beam. This is saying, for those x-rays, let's adjust their energy. More energy is more penetrating, okay? So you are remembering for MAS, you're remembering the 30% rule, which is irrelevant for right now, okay? Mass changes are direct and proportional. That's the important thing. Okay, 30% rule, by the way, with the mass was just to tell you that if you make a change, you better make at least a 30% change, okay, to show any difference at all, okay? But the most important thing about mass is it's direct and proportional to exposure. kV is not. kV is direct but exponential as it relates to receptor exposure. So let's give an example. Let's say I had a PA hand X-ray, okay? It's normally shot at 60 kVp at, I don't know, what's a mass number for a hand that you've used before? 10 mass? That's kind of a lot. We'll use it. 10 MAS, okay. Let's say the hand was 4 centimeters thick, okay? You get this number, patient number 1, patient number 2 comes in. We want to do a PA hand, but now patient number 2 is 8 centimeters thick. If you changed mass, so let's take this procedurally. How much thicker is patient 2 compared to patient 1?
Double.
They're twice as thick, right? But that's a special kind of twice as thick because they're exactly 4 centimeters thicker, right? So how much thicker is patient 2? 4 centimeters thicker, right? And what's the 4 centimeter rule? Double what? Double the radiographic technique. Okay, so the 4 centimeter rule. You guys are right, by the way. You're not wrong, but there's more to it. For every increase. Okay, so this word technique. Okay, technique is referring to the settings that you make. Mass, kVp. Those are primarily what we mean by when we say technique, okay? So we say double the technique. You guys translate that to double the mass, right? You're not wrong, that's right, okay? So patient 2 comes in, every 4 centimeter increase, double the technique. You can do that by doubling the mass. So you can come to patient 2, and you can give patient 2 60 kVp, because you don't need to change that, right? And you can give patient 2, what would you give them for MAS? 20, because they're 4 centimeters thicker than the previous patient. So double the MAS. Okay? We'll call that like option 1. Option 1. Let's read what this says here. Let me give you what I say, which is equivalent to what the book says. The 15% rule says a 15% increase in kilovoltage is equivalent to doubling the mass at the image receptor. So at the image receptor, 15% increase in kV would double the receptor exposure, and or a 15% increase in mass would also, a doubling the mass would also double receptor exposure. 15% rule says 15% increase in kV is the same thing as doubling the exposure at the receptor by using mass. I can change mass like I've shown here. This person gets one image, going to be a good image. This next person who's 4 centimeters thicker is also going to get an adequately bright or dense image. It's going to be the same. These two images should look the same with brightness density, okay? However, I can make the change to doubling technique without changing mass, okay? So the technique is take whatever the kVp was for the original patient and add 15% to it, okay? So you take 60 times, and there's two ways to do this, they're equivalent, but let me just show you. Take 60 times 0.15, okay? And just, you get a number from that, I think it's 8, but let me just do it real quick. 9, there you go, see? That's why we do the, on the calculator, 60 times 0.15. So 60 times 0.15 is 9, okay? So then you take 9 and you add it to 60, so 60 plus 9 equals 69. That would be the new kV setting, okay? The other and exactly the same, is not even different at all, but it takes less steps. Way to do this is take 60, multiply it by 1.15. Just saying, take it, multiply by itself, plus 15%, which is just one less step. Gives you 69. These are two ways to get to the same exact answer, okay? They're absolutely equivalent. You're just taking more than one step with the first way, 2 steps with the and only 1 step with the second way. So, option 2 for patient 2 is 69 kVp at 10 MAS. All 3 of these are going to give us the same exposure at the image receptor. Meaning all 3 ways to do this, thin patient at that setting or thick patient with those 2 options, are going to give us 3 different images with equal brightness density. Okay?
So the machine doesn't reflect those rules, like the 15% rule, or
no,
it's all on graphs like
it's
that?
all on graphs, yeah. I mean, now if you've got automatic exposure control or anatomically programmed radiography, which is punching in what body part you're going to look at, the software can do all these calculations for you, but you need to be able to do them without the software. So the smarter computers, smarter software can do this. You still have to tell it what the patient's information is. You have to give it a thickness, for example. So, how do you know that thickness? You measured it, right? And then you just use the rules that we've gone over to make the change. Okay. Here's the takeaway though. Okay, and I think I can show it with a little graph that they like to use here. Okay. Yeah. All right. So let me give you the takeaway from here first. Okay. So let's look at this one. This is a graph showing you some data from some experiment done, dosimetry measurements from a lab back in 2013, okay? So they took 4 exposures, all right? And the first exposure they did, doesn't matter what they took an x-ray of, doesn't matter at all, okay? First exposure was done 70 kV at 16 mass, okay? And they got a radiation reading, so you can use a little Geiger counter and you can measure how much radiation the beam emits, right? So this is ignoring like images, anything like that. We're just measuring the amount of radiation put out of the X-ray tube, okay? And they measured 146 millirad, okay? That's the unit millirad. Don't even worry about what the unit is because it doesn't matter. All we're looking at is relative numbers here. They got 146 millirad. They took a second exposure, raised the kVp by 15%, and cut the mass in half. So briefly, What does raising the kVp by 15% do to the image receptor exposure? Doubles it, right? What does cutting the mass in half do to image receptor exposure? Is it raise exposure or lower exposure? Lower by how much? Half, exactly half, right? So one change, the 15% kV increase from 70 to 81, doubled receptor exposure, and then they compensated for that by cutting the mass in half, cutting the receptor exposure in half. So this one, right here, had the same receptor exposure as the first one. 1 and 2 have identical receptor exposures, okay? But look what happened to the measured radiation. The first one measured 146 millirad. The second one only measured 98 millirad, okay? The second one had less radiation, even though the image receptor would have seen the same thing, okay? 67% of the original exposure. We're down 33-ish%, okay? 34 is what they say, okay? We're down quite a bit. Our measured amount of radiation is down, okay? We've lowered the patient's absorbed dose, but kept the receptor exposure the same. That make sense? Okay. They do it again. Look, they go from 81, add another 15%. That takes us to 93. And then they take 8 and cut it in half. So 1, 2, and 3 have identical receptor exposures. You're sort of getting the theme here, right? Receptor exposure will be the same for all of these, but we're down again. Okay, we're down another 32%. Okay, from here to here. Yeah. We're lowering patient exposure each time. Why? Why is patient exposure going down, but the receptor exposure is staying the same? What are the two changes happening? You're taking X-rays out of the beam by lowering mass each time, right? So you're actually lowering the amount of radiation, but you're increasing the beam energy, right? Raising the beam energy and lowering the amount of radiation actually emitted from the X-ray tube, if you do them the right way, you can keep receptor exposure identical, but lower the patient's exposure, okay? In the upcoming talks, we're going to talk about how we can take like existing technique charts and adjust them all so that every exposure lowers the dose to the patients, right? If you could take all of these and just do this one time, 15% up in kV, half the mass on your entire technique chart, then every radiograph you take will be about 40% less exposure to your patients. 40% for all intents and purposes might as well be half, right? You cut your patient exposure in half for every x-ray you'll ever take. Every patient now gets half the amount of radiation. That means patients coming through your office are going to get half as much radiation as patients going through maybe some other office who didn't take these steps, right? That technique is called variable kVp technique charts, and it's something that we'll talk about in the upcoming talks that we'll do. But that's the idea here, right? So to summarize some of that, right, a 15% increase in kVp, on average, increases patient exposure by about 30% if you don't change anything else, okay? But if you cut the mass in half as well, right, patient exposure gets cut about 50% by cutting the mass in half. Net reduction, something like 67% of the original exposure, roughly. Patient exposure goes down when you raise kV and cut MAS. You have to keep in mind the one important thing. What is kVp control? Penetration, and how does it control grayscale? Or does kVp control grayscale?
Yes.
Yeah, right? So by changing the kVp, you're affecting all these things, receptor exposure, patient exposure, and it sounds good, but if you change it too much, you end up affecting contrast, okay? So roughly speaking, we can get away with this 1 or 2 times, okay? Like 1 or 2 increases of 15%, and subsequently cutting the mass in half at those same times, and still have usable images. But if you do too many steps of increase, you start to destroy contrast, okay?
I have a question.
Go ahead.
Well, no, like,
Yeah.
prior, like I asked you, like, that question, how many times can you?
Yeah, 1 or 2.
And then you answered it like some completely different.
I might have. I don't remember what I said. But so, you can get away with about 1 or 2 15% increases in kV while subsequently cutting mass in half. So with this one, that's good. that's also okay. That might also be okay, right? But you start to get to this number, right? 3 steps of increase in kV with subsequent mass changes going down. This high kilovoltage starts to really degrade the image contrast, right? We start to lose, remember at the high ends, the extreme ends of contrast, we lose visibility. Either too low of contrast or too high of contrast, kVp being too high or too low, we start to lose visibility. So at these extreme ends, you're not going to have as much visibility as you would like. But the lesson is that you can get some net decrease in patient exposure by adjusting kilovoltage and up and mass down. That's everything I want to do for today. I'm a little bit past my time anyways. So